Hi, Chemistry 370. Welcome to my presentation. Thank you for coming. My name is India Eichelbach-Goss, and my topic today is ocean biogeochemical changes that have resulted from climate change. So today I'll first cover a variety of climate change related effects that have been observed in and predicted for the ocean's biogeochemical cycles. First, we'll view a map of where oceanic changes due to climate change are observed in the ocean, and we'll briefly discuss some of the methods that are used in these places. Then some background information will be provided with respect to ocean warming and the solubility effect and the stratification that result. After that, we'll look at trends in CO2 uptake by the ocean acidification, and how carbonate chemistry, as well as the solubility of oxygen, is affected in surface waters. We'll move on to how oceanic oxygen trends, and we'll follow briefly by how changes in nutrient concentrations will affect net primary productivity and the biological pump. Then some conclusions will be provided at the end, followed by some time for questions. So first off, as you can see in this map, there are 33 planned and existing ocean observation stations. And this map illustrates how most of these stations are located relatively near to the land, near the coasts rather than further out in the ocean, which is so that they can undergo regular maintenance. But this indicates that their measurements may not accurately represent the entire ocean. In fact, only an estimated somewhere between 9 and 15% of the ocean is represented by the existing network of observatories. As for some terminology, the word footprint refers to the area that the observations and the data collected by an observatory are said to represent. The largest of these footprints belong to stations that are located in the Arabian Sea, in the North Pacific and Southern Ocean, while the smallest footprint of one of these stations is in the Mediterranean Sea. It's also important to note that the trends detected by these observatories are easily skewed by gaps in the time series. So, for example, if you measure for 20 years and then you don't measure for 5 years, and then you measure for 20 years again, that 5-year gap can really throw off trends that might be detected otherwise. And another thing that's important is that about 14 to 32 years on average are needed to detect climate change trends from changes that would just be due to natural variability, which would be conditions like the El Nino Southern Oscillation or the North Atlantic Oscillation. One thing to note also is that less time typically is needed for trends in the low latitudes and the Arctic regions. And some methods of measurement and calculation that are used by these ocean observatories are linear trends in annual values of the variables for the simulation period 2006 to 2100. That is calculated using generalized least squares regression. And there's also frequent use of model analysis as well as satellite observations compared to each other. 8 variables typically are measured, and those are average sea surface temperature, surface pH, surface concentration of chlorophyll and concentration of nitrate, primary productivity, total export flux at 100 meters depth, and the annual average concentration of oxygen at the 200 to 600 meter depth range. So this will be a pretty short slide since our peers have already done such a good job explaining these effects of ocean warming, but I just wanted to briefly go over the fact that these effects are largely the reason that the ocean's biogeochemistry is changing, which of course can be credited to climate change. So we know that global warming makes ice melt, and it also causes thermal expansion due to ocean warming, and that all causes sea level rise. We also know that stratification, which is defined in this slide, is changing throughout the ocean. It's increasing in the top few hundred meters, while in the abyssal zone, the stratification is likely to decrease. We're also familiar with the solubility effect. That means that warmer waters hold less oxygen, and carbonate and calcium carbonate are more soluble. This information is all from the IPCC AR5 Working Group 1, Chapter 3.8. So, as for carbon, the ocean is a very important carbon sink. CO2 is pumped into the air. A lot more has been pumped into it recently due to anthropogenic causes such as fossil fuel burning, and greenhouse gases, aerosols, things like that, which we've already discussed. A fun fact is that the ocean holds about 50 times more inorganic carbon than the atmosphere does. So that just shows how important it is as a sink. And as the concentrations of CO2 have risen, so has the ocean's strength as a sink. So there's a parallel there, and it's likely to keep increasing, but scientists are unsure as of how much this can continue. So as we've discussed in this course, when CO2 concentrations increase, that leads to decreases in the pH, so that makes the ocean become more acidic. And according to the IPCC AR5 Working Group 2's special report, The Ocean and Cryosphere in a Changing Climate, in a recent 25-year continuous study period, the pH of the ocean's surface waters decreased by about 0.013 to 0.03 pH units each year. And this leads to pretty disastrous effects in marine ecosystems as the carbonate becomes undersaturated and bicarbonated is favored. Next, we'll go over trends that have been observed in ocean oxygen. And this is because surface water oxygen levels are controlled by a combination of production during photosynthesis, temperature-controlled solubility, and air-sea exchange, all of which have been affected by rising temperatures. So that's just the surface waters, but as for the deep ocean, the measured oxygen fluctuations are not exactly the same. The changes here are mostly impacted by changes in large-scale ocean circulation, but overall, the ocean is losing oxygen. And as I mentioned before, changes in increased stratification in the upper ocean has a variety of effects. So here we look at how nutrients like nitrate become trapped in the ocean's interior, which leads to reduced nutrient levels in the upper ocean. However, we might note that there is an exception for iron. All of this can be explained by looking at the schematic at the right. It goes into much more detail about how these changes in nutrients will likely cause a decrease in net primary productivity over the global ocean. This will affect countless other systems, such as causing a decrease in the biomass of marine animals, as well as threatening the livelihood, income, and food security of many of the world's people. However, there is a possible exception to this net primary productivity decrease in the Arctic regions. So to summarize and conclude, greenhouse gas emissions are causing a major environmental issue that's posing a threat to natural ecosystems and humans alike. And this can be seen by observing changes in the ocean's biogeochemistry. Although the current network of ocean observatories is representative of only a small portion of the ocean, and long-term continuous research is needed for clearer trend detection, we can see with some certainty that the effects that are going on in the ocean due to human activity are not positive. And the main biogeochemical changes of concern are those involving ocean acidification and CO2. carbonate chemistry, O2, and nutrients such as nitrate that will affect the ocean's primary productivity. Thank you for coming to my presentation.